Let's talk about bubble sort algorithms. In terms of the algorithms, we are also going to look at the bubble sort code as well as the sorting analysis. Bubble sort is a sorting algorithm that iterates through a list, comparing and swapping adjacent elements. When comparing the adjacent element, just like selection sorts, if the second element is less than the first element, it'll do a swap. This is assuming that we're doing ascending order. Descending order is the same thing, right? Same idea. So bubble sort uses nested loop. Whenever you have two loops and doing adjacent comparisons of the elements, numerous swap are used to move element into sorted order. The other sorting algorithms that swap non-adjacent elements is often important for faster sorting. Bubble belongs to the adjacent sort or element sort using a pairwise. You ended up with a O of n square, making the algorithm impractical for real world scenarios. If we look at the algorithm first, I think it will be a lot easier to understand, how this works. You have this array here, representation 0, all the way through n minus 1. The outer loop starts from here, from the very top, and that is in red. The movement of your red arrow, starting from 0, is actually from top to bottom. So this outer loop here is top to bottom. What's going to happen is you will have the inner loop here represented in blue, going in the opposite direction. And this opposite direction goes all the way to the top. Bubbling is comparisons of the pairwise adjacent elements. Adjacent element means comparing ith and ith plus 1 location or ith minus 1. Depends on where you look at it. If we follow the route here, this is from n minus 1 towards that 0 directions. You'll be comparing maybe the ninth elements against the eighth elements, and then the next one is the eighth element comparing against the seventh elements, and the seventh element against the sixth element, so on and so forth. So this is the bubble we're talking about here. And that bubbling action for the inner loop, which is represented in blue here, is from bottom to top. You have this one outer loop going from top to bottom, and the blue one, the inner loop, that goes in the opposite direction of the other one. This is the red part. And the blue part is your inner loop, which is the bubble up portion that we were talking about. Every time this thing moves down, that means the one that we had before has already been in the right place. As this red moves down to here, everything on top would have been done already. So like by the end, as you move the red or the outer loop down further, this entire array would have been in the appropriate ascending order, starting from the 0 all the way to n minus 1. This is essentially the bubble sort algorithm. In the very beginning, this red part, which is the outer loop, is responsible for orchestrating the order of the sorted elements. This is iteration number 1, iteration number 2. This red part, the sorted number of elements in this case is 1, in this case is 2, in this case is 3, and in this case is 4. So this is the outer loop in red. We also have an inner loop. So this inner loop is the bubble part that you see here. So let's just use the blue one. So this bubble part goes up and goes up and it goes up n minus 2 times because we're doing comparisons here. When you do a pairwise, you got to always remember if you have n number of elements and if you represent this n number of elements in the array, it will be 0 to n minus 1. But because we're doing pairwise, essentially the number of elements that you need to look at or iterations you need is actually n minus 2. 6 against 12. So remember, we're doing ascending order. So the smallest one needs to go on top. So 6 and 12. When you do a comparison, 6 is obviously smaller than 12, so we need to swap. So the very first one swaps. The next up is going to be the third element compared against the 2, the second index element. And this one is okay, so we don't swap. But the third iteration calls for index at 2 versus 1 at index 1. So swap happens, so on and so forth. So as you can see, every time you see a double arrow, that's when the swap happens. This guarantees at the end of the very first iterations in red that you have one element that is in the rightful place, which is 0. The second iterations happens all the way up until this point, from here to here. So you got one last to look at because 3 is already in the rightful place. You don't want to touch it. Now you have n minus 3 elements to iterate through from inner iteration perspective. So every time you up one level, the second iteration from the outer loop calls for 2 swaps in the inner loop. At the end of the second iterations on the outside, you're guaranteeing having 2 elements in their rightful spots. and then third and fourth, so on and so forth. You keep track of the indexing and make sure that you don't get array indexing out of bounds here. So this is the bubble sort snapshot. This thing in blue is always sorted. You have a portion that is sorted and portion that is not sorted. So the not sorted part is here. This not sorted part is where the bubbling, the double arrow swap. Bubbling is going to be smaller and smaller as your blue part becomes larger and larger. So blue part is going to move down until the entire array has been sorted in place. And if you look at the code, which is also available in your sorts.java, so if you scroll down there, you see bubble sort here. So this is the bubble sort from the bubble up perspective. This inner loop going up there. This is O of n right here. Current from 0 all the way through size -2. So this iteration goes from 0 to size -2, which is necessary because if you do size -1, you're going to get index out of bound because we're doing a pairwise comparison. The bubble up goes from current, which is 0, all the way to size -1. This size -1 is the end index, which we know, and the starting index. If you look at this for loop is from the end index. Inner loop is the blue part, and the outer loop is going from here to here. So this is the outer loop, this part, and the inner loop is this part. So these inner loops go from end index all the way to the start index. Index can only go as far as 1. You're doing comparisons all the way to index -1 to avoid index out of bound. And you do a swap based on this attributes here. If you're doing this in the ascending order and for whatever reason your index are out of order, so you do a swap from the bottom to up. This is bubble up in the blue directions. The bubble up guarantees there's one spot that is in the rightful place. In the beginning, that rightful place is this thing in pink. And then the second iteration is going to guarantee the second element be in the rightful spot. All this while, you're bubbling up to the last pink area. This part is O of n. So we're going through n side, right? Basically whole size. Now the second part is interesting. This is exactly what we have and when we do a comparison in selection sort. The number of comparison is always one less. You have n-1. The next one is going to be n-2. There's less and less. This pink area is going to grow in this direction. So there's less to compare all the way to +1, +2. Using the Pythagorean principle in arithmetic, the number of comparisons here is actually n times n-1, the whole thing divided by 2. So this is going to give you n squared minus n, the whole thing divided by 2. And we really don't care about this part either. So this is going to give you O of n squares. This entire comparisons is very similar to selection sort. You get n-1 comparisons the first time, n-1, so on and so forth, and that's basically O of n squared. So both bubble sorts and selection sort requires the same amount of work. Both are impractical. As we see, the next one, insertion sort, is just as bad. We're dealing with nested loop. The efficiency is not increasing. It's just going to be exponential of